This is what we're going to be doing. Let me see if I can open the browser. I did yesterday have a bit of a quick session just off stream where I merged a pull request that was from Jordan, who basically really you know really likes the project and kind of wanted to contribute a little bit here and there. So, and what he did is basically we separated. He separated all the visualization stuff into a separate module. There's a quirk export, but this needs to be reworked because this was still under the assumption of we have gates as matrices, and so you have a gate that's applied to certain qubits, and you can the idea is you can record the application of gates, and then because quirk actually will require you to keep the to know what the circuit is, not just the state, right? Remember that everything else that we do in terms of printing stuff is we printing a concrete state. We're not printing a set of gates. So um, let's go. Yeah. So what this means basically is that now we have this file. So we changed a bit the way. Let me see, new terminal. Well, I finally ended up. So I finally ended up putting the actual gates in here. And there's two things that I want to do next. One is work on the rules and actually think about, so we have rules. How do we do everything else that you usually can do with a quantum circuit building library like Circ or Qiskit? Like at least we're missing parameterized rules, right? And then I also want to build this type of rules that are a bit more, sort of symbolic rules, right? Like that they go and match and assign values to variables, and then you can do things like entangling operations between registers, like a plus A or a plus B, like add the value of the top register to the bottom register and stuff like this. Um, so we'll have to. What I thought I'd do is I just literally actually have classes. Like I just have, I think the best thing to do here is to have basically a sort of the operation class. Mm, mm, Let me share in Twitter. So I wish there should be something more original. Building parametrized gates or operations. Cool. So I wish I kind of had the I don't know what I wish. I don't know what I just said. Okay, this is definitely not the browser that I want. I want the other browser. There you go. We'll actually open Jupyter and go to notebooks and go to testing. So yeah, so basically we now have we don't have the rules here anymore, and we just like have the X, and instead of just call it a X sub as X rule or H rule, just have X, H, and that stuff, right? So we import it from this file, from this module, and then the visualization is just on this module. That the basic visualization here that we had. And yeah, I know I started work on the factoring, but I feel like that's something I might just do off stream because it's a bit more boring. Um, and then kind of testing stuff is a bit more boring. And I thought I kind of had a will today to do something a bit more challenging or more kind of design oriented, right? And thinking about how you would do that, because there are two things that one could think of, which is in Circ, for example, you have the parameterized gates use SymPy, Well, and Circ actually distinguishes gates and operations by calling gate the actual definition, and the operation is the actual gate applied to a specific qubit. Um, Named qubit symbol. No, nothing about symbols. Common gates. Mm, okay, just literally as an argument, actually. Okay, rotations. Because I might just well use the same. Uh, okay, so there's exponents, right? And then there's rate. There's the angles. So the two things that we should have in there. So probably what this means is that we should have a um, maybe I shouldn't call these specifically gates, or just have it defined here, because here we have the hypergraph. Yeah, probably have it defined in here as well. So kind of have, so here we have the node class, and then we can have also basically the class. Um, do I call it gate? I'm a bit hesitant to use the word gate because it's got this very specific, qubit level kind of thing. Uh, but if I call it operation, it can be, I can call it operator, but that's also a bit overloading, stuff like that. That there's the operator concept in physics and in quantum mechanics. Yeah, I'll go with gate, but I might really change these. Um, and so the initialization of the gate. So what is the gate gonna have, right? Um, so the gate is gonna have basically the gate's gonna have a like a unique identifier, right? Which is, let's say, these here, which is going to be internal as well. Make sure that, one can refer. Yeah, I guess so. Just for serialization, maybe exporting and stuff like this, I think that's just good practice. So, so the unique identifier will be here, and then what you also want to have is, yeah, you want to have basically um, the rules will be defined and given by the gate, right? So it'll be like a function that just says get rules, and that basically, um, or just initialized. I'm not so sure what's the best practice there. It's like, what's the point in making it a uh, sort of a getter instead of just, mm, okay, because then it's not really. This is basic inheritance and stuff like that, right? So what I want to do is that then I want to define, a class, X, Yeah, do I want to do this? No, I don't want to do this. I definitely don't want to do these. Um, or how is it done? What's the design pattern that they use in Circ? Like, is I think Circ GitHub. So, for example, from Circ Ops. Okay, so these things are defined like that. Circ Ops. So they are in operations defined. Gates identity. Okay, so uh, control gates, tests, the wait gate, arithmetic operation, common gates. So what do they do? They no, they're actually classes. Okay, so they're actually classes. Uh, and then they have apply unitary, act on. So they it kind of makes sense because they've controlled. Hmm, phase exponent. So they actually, it's like, yeah, so there's a, so they define it as a, they define these things as classes. Um, and then there's probably a, uh, gate features, single qubit gate. So there's like stuff they inherit from these generic gates, right? If I, the stuff they inherit from these generic gates. So actually, what I should be doing is I should be building it, sort of bottoms up. So not having it here, but actually really, really defining the gates here, right? And say, um, so really kind of have the, hmm, the X. I'm thinking, how do I name this? The X gate, X power gate. Kind of. Uh, then the rules, the rules would be these ones, so they can't be changed. That's probably the best. So this would be like, get rules. This would be return these, right? So that returns uh, that returns the rules for the X gate. Um, actually, just like that, just the rules. So return the rules. Mm, there's no UID that needs to be passed in here. That makes no sense. I think. But what does make sense is how do we implement the mapping, right? So how do we implement? So here's the rewrite thing, right? So this rewrite stuff is basically, um, it's got an input map. So what we can say is the input map actually, the input map actually is given to the gate. I like the design pattern. Um, I like the fact that you can. Where is that? Uh, where's it? Where are these just Pauli gates? This is the Eigen gate, by the way. How do I implement tests? Identity, Pauli, common gates, controlled operation, dense Pauli. It's just these Pauli gates. There you go. So, so you've got, for example, um, class Pauli, right? Blah blah blah, and then they have the on, right, which is like this is the mapping, right? So returns an application of this gate to the given qubits. What does this do? It returns single qubit Pauli string gate operation with qubits 0. Um, yeah, yeah, the mapping is stored, right? So that's what it does. The mapping is stored, and mm, and then, but then how is the circuit built? So how's the application then run? That's like I don't know. Um, I don't know what are the advantages of these, because then you have the circuit, and then in the circuit you basically add operations that add on that operate on qubits. So a circuit has a set of operations that know where to go. Um, and here, the concept of the hypergraph thing here is to just be able to work at the operation level, right? This is not about like building a circuit and letting it run and see what happens. It's about like, I apply transformation. I want to see what the result is, and I do this kind of like rather on the fly. It's not about running shots and whatnot. So I'm not so sure this way of working with it would feel right. Like I'm working with a hypergraph, and I just say, hey, I want to apply this gate to these queries, and so it's not that I want to create. I think that stays probably like these. So you know, um, but I still am. That's still why I'm a bit hesitant to implement it. Like to implement this whole thing really as a class. I'd love to just have. I'd love to just have it flat, like plain. You know, it's not so sure. I'm not so sure about the class thing. Like, I'm not really not so sure about the class thing. Like if I have the X gate in here, so this is the it's sort of the rule object or the object that defines the X gate. It's got a gate. It's got a gate name. Call it name, not gate. So I'll call it name. Name. And I think where was that used? yeah, here only. So call it name, but then I think it just should have like a params, but yeah, just simply like a params thing here where you kind of, define you define a you just define a list of parameters. And it should be sorry, it should be no, it should probably be just just an exponent, right? An exponent, which is just 1. So these will be a value from 0 to 1. And then it can also have an angle for phase rotation, or just rod, which, like, I don't know if it's something that we just want to have a normalized way of specifying that, like also a value from 0 to 1, like how much you want to rotate. Um, yeah, because we're not restricted to using linear algebra stuff, so we don't have to now, do this whole thing. It's just, but that rotation is also not, because, so it's a match and replace kind of concept. That's how it started, right? So you match a pattern and you replace it with another pattern. Now, this is indeed an actual state. So if I wanted to specify that what I want to do is I want to um, do an exponent or something, I think that's definitely not, I think this is not even needed like these. I think this is just something that we have to, for example, let's try to do the square root of x, right? So square root of x, gate, right? So the square root of x, what it does is it turns, so it turns a 0 into into these like half plus half I, 0 and a half minus I, and the 1 into, yeah. So it basically, it turns a 0 into a half plus half, is that j, I think? J, or I don't know, how do you define that? And so you're actually defining these already as part of the rule, right? So yeah, so I think actually there's just no need to specify these things. Mm, yeah. So you're saying you're doing it like these, right? Does this work? Or so, oh, sorry guys. Square root of x So so that like it's hard coded. If you want to have a gate that is called, like the you know x the x with an exponent, right? What you wanna do is you wanna have a way with symbols specify these and say that yeah, this is when SymPy is needed, right? So and this is when this method is not only gonna have an input map, which we can call qubit map, a qubit map. So input map replaced with qubit map, but it's also going to have a which can be empty. It shouldn't, yeah. Cascades must apply at least to one operation, and then you can have a params map, so a map that kind of maps parameters, right? And what this is going to do is the rule actually should declare some parameters, probably, if so, right? Yeah. So the rule should say, look, I've got these params, which is these parameters, which is basically an array of symbols, right? And how does SymPy look like? So first of all, how do we install SymPy? How do we get SymPy installed in here? So is it just SymPy? Just want to install. Is it just like pip and stuff like that? Anaconda, Git, other methods. Can I not just install these, with pip? Yeah, pip install SymPy. Okay, so SymPy, and we should add this in the requirements, right? SymPy, and I don't really know what version 1.7.1. Yeah, let it be this way. So SymPy is needed, and then basically here we need to import SymPy. SymPy as SB. And so what we do here is probably we just have to declare symbols, right? So we have to go and say dear tutorial, just the basic exercises, introduction, symbols. Symbols X, okay, yeah. So it's basically, so you can just, okay, symbols X, yeah. So symbols, just symbols, right? Can I do that? I can just say, and the symbols, and then we'll just do A. You basically declare them with symbols, right? So you say, look, just, just one symbol in this case, which is, the exponent, and could be A, right? SP symbols A, and then what we want to say here is that we want to apply a it's an exponent of these, right? I mean, exponents would be easy because it's just apply. Mm, it's like applying the gate twice, right? Mm, because now I'm a bit afraid. I don't want to get into linear algebra. You know what I mean? That's the problem. But I mean, I have to. Like, there's no way if I say I want to apply half of the X gate, right? That I go and even if it's not that, even if it's just a rotation, let's just do a rotation. Like it's just got to rotate the thing. Like there's no sense. I mean, actually, I mean, there is, right? I could compute, or I could think of in general what this expression is, right? That you turn um, the qubit into, but it's not, that is not somehow, it's not straightforward. Like what it means, right? Like what does it mean if you have like a quarter of a rotation? A quarter of an X gate. Well, it rotates 45 degrees. So you have in linear algebra, that just maps to a certain matrix. Then you multiply the stuff and there you go. And you obtain what you can see here that says, transform 0 into this and 1 into that, which is ideally what I'd like to have like intuitively defined with a rule that I can give it a parameter, and this parameter is then, when it's then matched here, right? Because I can then reuse the rules and I don't have to compute them every time the same. Another story will be when we um, when we deal with the parameters in the matching side. Like these symbols won't need to be declared because the symbols are just basically populated on sort of on the match pass. So once we're passing to match things, and we're populating the symbols per hyperedge and all that stuff. So, but this is because it just brings me to an essential question, which is like, if I don't rely on linear algebra, do I need to rely on the state vector formalism at all? I mean, even for one qubit, right? But I gotta have a model there at some point. And if it's not a simple state vector, then what is it? Like, I don't know. I think that's something. It's sort of um, it's one of these things where I can't go beyond that, right? So, but that's definitely a problem with the rule definition, which is that um, when you've got matrix gates defined and modeled as matrices, it's easy it's easy to think about the square root of a gate, to think about the power of a gate. When you have them as rules, like, yeah, you could say apply these rules 3 times, right? But you cannot say apply these rules a quarter of the time. Um, and we're not operating, we're just replacing stuff. So but anyway, so what you would be doing here, right, is if your match is 0 cat, then you would do something with it, right? So you would still take A and like multiply, like I don't know, just multiply it, just to say some stupid thing, right? Just operate that with 0, right? Like you could think of, just doing something like these, which it just makes no sense, right? But like you have that basically symbolic expression, then because you're matching the symbols, then you can do that. Um, uh, but is a symbol, are symbols needed for these at all? Are symbols needed like these at all? Um, because I could just as well. I mean, definitely symbols are needed for the sort of the more arithmetic kind of stuff. But like here, I could have just well define um, a list of keys, basically a list of keys. Uh, like I could just say, so this is a list. This is basically a dictionary where like you've got something like this by default, right? And so what you will have here is you'll just have like params. Yeah, but that's not something you can do, can you? Can you just say, can you do something like this? Like, does something like this compute at all? Let's try. If I just initialize an object and I call it like you know um, result, basically non param basically you know um, no, so param basically non, and then result is basically self dot self param times 2, right? And if I now say a param equals 2, and then I say print, probably that doesn't work. Yeah. Self is not defined. Yeah. Oh, what? Yeah, of course not. But can I just do like this? That's not defined because I'm defining it. So that doesn't work. This kind of stuff doesn't work. View, edit, delete cells. that doesn't work. So we'll have to keep the symbols. I think that's what makes sense. We have a symbol declared here, and then we have a symbol that is used in here, right? Um, but also, I'm not so sure. I'm not so sure if this is something you can do either. Hmm. Hmm. Because that might as well just be the reason that kind of requires me to have a class to have these properly implemented. Because I mean, it's defined here, right? So if I import SymPy as SP, and I do a clear output thing here, can I do something like this? Let's try. Yeah. Got SymPy. Come on. Oh, God. Something's wrong here. In terms of what? Rules. Yeah. Yeah. Clear output. Ah, this is also not gonna work, but let's just say replace with 0. Replace with A. Okay, so I'm just testing. If this way of defining rules works, that I define that it's self-contained. So within the object I define the parameters and symbols, and then I use them in the rules. Whether that is recognized at all. SP is not defined. SymPy as SP. Oh, oops, oops, oops. Mm-hmm. Does it work? No, name A is not defined. Okay, so it doesn't work. Um, so I'll need to go with objects. I'll need to go with objects. And I'll need to go with objects, and then even the rules will somewhat be different, right? Because I cannot declare symbols, so I have to declare the symbols basically up front. Yeah, I have to declare the symbols a bit upfront. It's just this is really just a technical detail, right? Like how to implement that. But so out of all these, I will have to go with. I will have to actually go with a class, and then well, it's like I don't really have to, but I have to. Because then it's more self-contained. Otherwise, I gotta define symbols for everything in here, make sure there's no clashes, and as far as I like to keep things sort of flat and simple in terms of, flexible and just have like sets of rules and stuff like that. I think I need to go with the class, and then this class is gonna have a cube map, it's gonna have parameters map, and it's gonna have the rules. So we will just pass um, we'll just basically pass the operation here. Um, which kind of this can be, the way that the operation is initialized, right? So, yeah, cool. Maybe it doesn't feel super productive, but at least it's a bit of a kind of from a design perspective, some more clarity. Awesome. We'll leave it here. See you in the next stream.